Can everyone hear me? All right. Hello, my name is Savitha. This is my presentation on our paper, An Empirical Evaluation of Property-Based Testing in Python. This work is done with Michael Coblenz, and we're from UC San Diego. All right, let's get started. So, property-based testing was first popularized in the functional programming community with libraries like QuickCheck, but now it has spread to other languages like Python. And what property-based testing allows you to do is test multiple inputs with the same test body. So in this example, we see a property-based test written in Python using the library called hypothesis. And we have this test of this list max function, which finds the maximum of this list, and then we check that that maximum value is greater than or equal to every other element in this list. And with every property-based test, there's two components. The first one being the generator, and this is what actually produces all of those inputs. And then we have the property. And this is what we check when we're working with, when we want to assess our test. And hypothesis is very popular in Python. So there was a 2023 survey by JetBrains, which found that around 5% of the developers they surveyed used hypothesis. And if we tried to extend that to the entire population of Python users, that ends up being around 500,000 users. However, property-based testing can be difficult to actually do in practice. So in this example, we have our PBT version of our list max method, and then we have a regular example-based unit test version. And in our example-based unit test, we have our specific list that we're working with, and we can check the exact value of our max is 8. But if you look at our PBT, you might notice that this property doesn't actually assess the total correctness of this max function because we don't even know if that max is going to be in our list itself. So sometimes it can be difficult to come up with properties that effectively test all of the things we want to know about a particular function. So because of these difficulties, and also that it can be difficult to just come up with these properties, and it takes a long time to write a property-based test, we ask the question of should we actually recommend developers that currently just write unit tests to write property-based tests? And so from this, we have 3 research questions. The first being, how effective are property-based tests in comparison to unit tests? And also, what is the computational cost of using PBT? And if they end up being effective, what are the kinds of property-based tests that people should actually write? So looking at this first question, we're asking how effective are property-based tests at catching bugs when compared to unit tests? So what we've done is an evaluation of effectiveness that shows that property-based tests are around 50 times better at catching bugs than unit tests. So there are many ways that you can evaluate the effectiveness of a test suite. And one of the ways that you might be familiar with is with code coverage, which shows that if your tests cover a majority of the code, then your test suite is going to be more effective. But an alternative method is through mutation analysis. And the underlying idea of mutation analysis is that a good test suite should fail anything except for what the code currently does. So we have this really simple example function where we sum up 2 arguments and then return that sum multiplied by 100. And so a mutation on this source code would change one of these small aspects of this program. For instance, one of that could be changing plus to minus, or you can also change 100 to a negative 100. And these small changes in the source code are what are called mutations. And what you do in mutation analysis is that you run your test suite on each of these mutations, and you try to see if any of your tests will fail. And if one of them does, then that means your test suite is more robust. But if all your tests pass, even when there is a change, then that means that your test suite is not as robust as you thought. And although these mutations seem very insignificant, prior work has actually found that mutation detection, being able to catch these small changes in the source code, is positively correlated with real fault detection. So we can use mutation analysis to assess the effectiveness of the tests in our projects. So in our experiment, we collected a corpus of Python programs that use hypothesis. And we tested 40 of them using this mutation analysis where we created 100 mutations per project. And what we found is that PBTs found mutations 11% of the time, while unit tests found mutations only 0.24% of the time. And the kinds of mutations that they find are pretty disjoint, with only 15% of the mutations being found by both kinds of tests. And when we ran a chi-squared analysis, we got a significant result with an odds ratio of 52, which shows that property-based tests are 52 times more likely to find a mutation than unit tests. And you can kind of interpret this as saying, like, with the property-based tests, you get the same detection power as 52 unit tests. And we also considered code coverage in this. So when we controlled for code coverage in a project, we found that we got similar results with a similar odds ratio. So we see that PBTs are pretty effective at catching bugs, especially in comparison to unit tests. But a property-based test also runs hundreds of inputs. So what is the actual computational cost of using a property-based test? And especially because people run these tests in continuous integration pipelines, it's especially important that we're able to test things efficiently because people are running these all the time. So our next question asks, how does the bug finding efficacy of property-based tests relate to the number of inputs used when executing them? And so we conducted a parameter sweep experiment on just our property-based tests in our corpus, and we found that over half of mutations were found with just a single input, and 76% of them were found within the first 20. And this can be due to how the back end of hypothesis generation strategies work, but it could also be indicative that thinking of correctness as properties instead of specific input-output examples could be a reason for why the tests that people write with PBT are better at finding bugs. So we've seen that PBTs are more effective at finding bugs than unit tests, and that the computational cost of them is less than what you may expect if you were just considering them as hundreds of unit tests. So our final question is, if they are in fact effective, are there specific kinds of property-based tests that people should use? So there have been many informal guides on how to write properties for PBT, and these are 3 examples that are linked in the hypothesis documentation. So we started with these kinds of properties to see if we could automatically detect when tests correspond to each of these recommended kinds. So we came up with our third research question. We asked, what kinds of properties do Python developers check in PBTs? And so we came up with a categorization of PBTs by property, and we have definitions for 12 categories, and a tool to automatically classify PBTs into these categories. So if we recall, we have 2 pieces that are in every property-based test, a generator and a property. And what we noticed is that in order to be a property-based test, every PBT has a data flow from the generated argument produced by that generator to the actual assertion that's being checked. So we decided to use these data flow patterns to categorize our tests. So as an example, we're going back to our list max example. And if we start off with our list being generated, ls, we see that we get the max value from this, and also we look at every element. And we then compare the max to the elements of each of these. And so the overall pattern is what we call a bounds check. Now looking at something explicitly from one of our corpuses, we have this extended Euclidean algorithm test, which makes sure that when you have 2 positive integers, a and b, that you're able to find the greatest common divisor of this. So we start out with a and b, which are being generated as integers from 1 to 1,000, and then we plug it into this extended Euclidean algorithm, and then we receive d. And then from there, we check that a mod d is actually equivalent to 0. And because 0 is not related to a and b, we call this a constant, and we call this pattern a constant equality pattern. And so overall, we obtained 12 categories from this data flow analysis, and 5 of these are actually related to those recommended properties that we saw. So looking at the classification, we had around 492 Python projects in our corpus, and we categorized 94% of these. We also collected a set of 50 projects that were not in our original corpus because we used that corpus to develop this categorization, and we also categorized 94% of those. And the most common category in both of these corpuses are constant equality tests. But because we have all of these different categories, we wondered, are there certain categories of property-based tests that are more effective at finding mutations than others? So we conducted a similar evaluation of effectiveness as we did with the first research question, and we did find that some categories are more effective at finding bugs than others. So for all but 3 of the categories, we received significant results, and our top categories were the following: exception raising, which checks that a specific exception is raised; inclusion, which checks that some variable is included in some collection, and then type checking. So one thing to note is that because some of these categories had kind of sparse tests in them, we do run into a risk of sparse data bias in our odds ratios, so they could be inflated, but we still get significant results from these categories. So looking at the odds ratios overall, we see that we have most of the categories doing pretty well, but we noticed that all of the constant quality tests were pretty common in our corpus, but it is actually pretty middling when it comes to their effectiveness. So perhaps we do need better tools to help people write more effective test cases when they are using PBT. So going back to the original guiding question of whether we should recommend using property-based testing, I want to take a moment to say what this talk is not saying. So we're not saying that unit tests aren't needed. Oftentimes, you still want to use unit tests to check specific edge cases, and also certain things are just easier to test with a unit test than compared to a property-based test. And also, because our study is an observational one, we can't infer a causal relationship from writing PBTs and finding bugs. And for that, we actually need to conduct additional experiments which allow for an intervention. In addition to this, we also want to study the time cost of writing a PBT, analyze property-based testing generators, which we didn't analyze in our particular study, and also do a comparison with other languages. So overall, we have a categorization of property-based testing into 12 categories, and we've conducted experiments assessing the effectiveness of property-based testing. And we found that PBTs are more effective at finding bugs than unit tests when we use mutations as a proxy, and they also find most bugs within a few inputs. So this is a QR code to our paper, and feel free to ask me any questions.
Okay, thank you for the talk. I think we won't have a lot of time for questions. I see a lot of people queuing up. We might have one or two at most, and then I think it's a very interesting talk. You can take the questions after, to the coffee break after this session. So yes.
Okay. When comparing unit testing with PBT, one important factor is that since they are both written by human, how do you control how these tests are written? Could you elaborate on that point?
So we had the assumption that the same people were writing PBTs as were writing unit tests because we were looking at those written by in the same format. There is a possibility that they could be written by different people if we had looked at the GitHub contributions, but we made this assumption, so we think it is a fair comparison that the same people would be writing the tests for this project.
Thank you.
So another aspect in which you compare properties is how useful are the counterexamples.
Yes.
For example, we found that properties to check data type invariants aren't so good at catching many bugs, but on the other hand, if you do raise invariants, debugging that for a more complex property is far more difficult. So it's worth testing for those ones. But anyway, I wonder whether you have some sort of experience there. What are your reactions to this?
Yes, I think it is an important thing to look at, seeing how people use the results of PBTs. And I think once we do our actual human evaluation, it would be a good experiment to check how people use those. Thank you.
Thank you. We move